When you look up and see a massive overhead transmission line,
Hmm.
just cutting across the horizon, you probably just see static metal and wire.
Right, just steel in the sky.
Exactly.
Yep.
But what you're actually looking at is a financial behemoth. I mean,
Yeah.
whether you are an engineer prepping for a huge EPC meeting or just insanely curious about how critical infrastructure is built, we are thrilled you are here.
Because we're talking about projects that cost hundreds of crores.
Hundreds of crores, yes, where a miscalculation of just a few inches in a single tower placement can basically bankrupt a contractor or delay a project for years.
Absolutely. It happens more often than people think.
So the mission for today's deep dive, the one high-stakes question we're asking is, when a transmission line project has that kind of staggering budget, where exactly is all that money being spent?
And how do we stop the financial bleeding before it even starts?
Right. Today we are opening up a fascinating stack of engineering notes, design workflows, and case studies to figure out how digital engineering, specifically a platform called PLS CAD, actually changes the financial trajectory of these mega projects.
But right out of the gate, we really need to set the record straight on a massive misconception in the industry.
Oh, about it being a magic button.
Exactly. PLS CAD is not a magical cost-cutting button. You do not just import your survey data into the software, hit a button, and watch your budget shrink by 20%.
Right. The software itself doesn't save a single rupee.
It does not. Better engineering decisions save money. What this platform actually does is give engineers a highly accurate digital 3D environment so they can evaluate the route, the terrain, spotting, and clearance decisions well before construction even begins.
Because the biggest financial savings happen in the digital model, long before a single piece of steel is erected in the dirt.
Precisely. See, to understand how we save money, we first have to map out the financial anatomy of a 100-crore power line.
Okay, let us unpack this. From an electrical engineering perspective, the sheer volume of materials is just staggering. You have the CapEx, the capital expenditure. That is bucket number one.
Right. The procurement side.
Yeah, you are buying thousands of tons of heavy conductor cable, the insulators, the hardware fittings, and the OPGW, the optical ground wire that runs along the top for communication and lightning protection. And that is just the electrical side.
Yeah, and on the civil and structural side of CapEx, you are dealing with massive quantities of galvanized steel for the lattice towers, plus thousands of cubic meters of concrete and reinforcement steel for the foundations.
Not to mention the immense cost of land acquisition and securing the right-of-way.
Exactly. But see, CapEx is only the beginning. Bucket number 2 is the project execution cost.
The logistics.
The brutal logistics of building in the real world. We are talking about detailed topographic surveying, carving out access roads through incredibly remote terrain, and transporting heavy materials to completely inaccessible locations.
And the actual physical erection of the towers. Plus, the highly specialized, dangerous process of stringing the conductor wire over valleys and rivers.
Yes. But while CapEx and execution are massive, they are relatively predictable.
Right, you can put them in a spreadsheet.
Right.
But it seems like bucket number 3, the indirect costs, isn't that where a project actually bleeds to death financially?
Oh, without a doubt. The deadliest category. We are talking about design changes midway through the project, rework, clearance violations, and severe schedule delays.
So if we know these indirect costs are the killers, how does building a digital model actually prevent a contractor from getting slammed by them, say, 6 months down the line?
Well, it prevents those costs by forcing all the engineering disciplines to confront physical reality simultaneously. Indirect costs are almost always the result of a late discovery.
Give me an example of that.
Okay, so suppose a structural engineer designs a standard tower, but the civil engineer later discovers during construction that the terrain at that specific spot is actually a steep, rocky slope.
Uh-oh, so you suddenly need a custom leg extension.
Exactly. And if that is discovered during construction, you have idle heavy machinery, you have specialized labor just sitting around waiting.
And massive contract penalties for missing your timeline.
Yes. So by visualizing the exact constructability in 3D early on, we target all 3 cost buckets. We keep CapEx lean by only ordering what we need, we make execution smoother by planning access, and we drastically reduce those fatal indirect costs.
But knowing we need a digital model doesn't actually solve the initial problem, does it? If we want to stop bleeding money, we have to rewind to the very first decision made on any project.
Which is where to put the line in the first place.
Right. Route optimization. You have point A, point B, and a whole lot of challenging earth in between. In the traditional days, a bad route basically meant you were locked into a longer overall line length
Terrible terrain, a nightmare of highway and railway crossings.
and more expensive foundations. So how do we begin chipping away at that with digital engineering?
This is where PLS CAD becomes really valuable, especially when paired with modern LiDAR survey data. Let us take a practical example from the sources.
Okay, let's hear it.
Suppose you have an initial proposed route alignment of 200 kilometers. On a 2D map, it is just a straight shot, but when you pull that LiDAR data into the software, it generates a highly accurate digital terrain model.
So you see the actual topography.
Exactly. And you immediately see that your straight line goes right through a protected wetland, which, will delay environmental clearances by a year.
Right.
And then it crosses a severe mountain ridge requiring extremely heavy angle towers.
So the engineers tweak the path in the software. They bypass the wetland, route it through a natural valley pass, and maybe they bring the total route down to 196 kilometers.
Saving 4 kilometers.
Yeah, saving 4 kilometers.
Yeah.
But if you are listening to this and assuming that saving 4 kilometers is just a simple math equation, you're falling into the exact same trap most junior engineers do.
Oh, it is never a simple math equation.
Right. You cannot just take the average cost per kilometer and multiply it by 4 and tell the project manager you saved them that much money.
Absolutely not. Transmission line costs are fixed, they are highly discontinuous, and heavily dependent on the terrain.
Because it's not like buying fabric by the yard.
No, it is not. You might shave off 4 kilometers of overall length, but if that new 196-kilometer route forces you to make 20 sharp turns to avoid the wetland,
You have a big problem.
yes, you now have to use heavy tension angle towers instead of standard suspension towers at every single one of those turns.
And from a structural standpoint, those angle towers use significantly more steel and require massive foundations to resist the pulling force of the wire.
Exactly. It is more like planning a road trip. Shaving off 10 miles of driving doesn't actually save you money on fuel if that shortcut takes you through an expensive toll booth.
Or forces you up a treacherous mountain pass where
Yeah.
you are grinding in first gear the whole way.
Right. PLS CAD allows the design team to evaluate the route against the structural constraints of the towers, so you don't accidentally take the expensive shortcut.
You are optimizing for total installed cost, not just line length.
Which naturally transitions us from the macro level of the route alignment directly down to the micro level of the towers themselves.
Right, because once that optimized path is locked in, the next step is tower spotting.
Deciding the precise geographic coordinates for every single tower. And this is arguably the single largest opportunity to either save crores of rupees or completely blow your budget.
Because the terrain is rarely perfectly flat. If you spot a tower in a slight topographic depression, the wire is naturally going to hang closer to the ground.
And to maintain your statutory safety clearances, you are suddenly forced to use a much taller tower.
But wait, let me play devil's advocate here and challenge the conventional thinking. If these towers and their concrete foundations are the most expensive individual assets on the project, why don't we simply stretch the wire as far as possible?
You mean maximize the span length?
Exactly.
Yeah.
Maximize the span lengths and cut the total tower count from, say, 500 down to 450. Wouldn't eliminating 50 towers from the procurement list save a fortune?
It sounds perfectly logical from a procurement spreadsheet perspective, I will give you that. But structurally, it is a disaster.
Really, why?
Because of the physics of the sag tension chain. See, when you span a wire between 2 points, gravity pulls it down, creating sag. To stop it from sagging into the trees, you have to pull it tight. But if you stretch that wire over a massive distance to eliminate a tower, the tension you have to apply becomes extreme.
And as an electrical engineer, I have to add the thermal reality to that mechanical tension. We are pushing hundreds of megawatts of power through that conductor.
And it gets hot.
Incredibly hot. Due to electrical resistance, the metal expands. So that wire physically lengthens and sags even further towards the ground during peak operating hours.
It's like a giant thermal rubber band.
Exactly. So to counter that deep thermal sag over a maximized span, you have to pull the conductor with massive initial tension.
But here's the structural consequence of that. That high tension is constantly trying to pull your two towers inward toward each other.
Oh, I see.
So to keep those towers from collapsing, you have to design them with exponentially heavier steel members. And a heavier, highly loaded tower requires an enormous, deeply excavated concrete foundation to anchor it to the earth.
Wow. So by trying to save money on 50 standard towers, you have just forced the remaining 450 towers to become absolute Heavy-duty monsters.
Precisely. The cost of those massive foundations and the ultra-heavy structural steel completely wipes out any savings from the reduced tower count.
So fewer isn't always cheaper.
Never. And this is the core engineering reality that PLS CAD helps visualize. Optimum span does not equal maximum span.
So the goal is system balance, not just minimizing tower count.
Exactly. The software allows the engineer to simulate the wind loads, the thermal sag, and the mechanical tension across thousands of permutations to find the perfect balance. You're optimizing the mechanical system.
Okay, so we have optimized the route, and we have found the perfect sag tension balance for our tower spotting.
But the digital model still has to survive contact with the messy reality of the actual ground.
Right. Let's talk about clearances and the cost of late discovery, because every single kilometer of a transmission line is unique. You are crossing agricultural lands, rocky outcrops, and critical infrastructure like railway lines.
National highways, existing communication networks, and those crossings are heavily regulated. You cannot just guess the clearance.
No, especially not here. If we look at Indian infrastructure projects, for instance, you have incredibly strict CEA regulations, the Central Electricity Authority. They govern exactly how many meters of clearance you need above a railway track.
And those clearances change drastically depending on the voltage.
Huge difference. It is one thing to build a 132 kV regional line, but if you're building a 765 kV green energy corridor, the rules change entirely.
Because the arcing distance is much higher.
Exactly. At 765,000 volts, electricity wants to jump. It wants to find a pass to the ground. If that conductor sags too close to a railway gantry or a building, the current will literally arc through the air,
causing a massive, potentially fatal fault.
Right. So the air gaps required are massive, and the tolerances are unforgiving.
Which brings us to the nightmare scenario. Imagine a project designed purely on 2D profile drawings.
Okay.
The design is issued, the EPC contractor is on site, the foundation concrete is poured, and the tower is erected. Then, the site engineer realizes that at maximum operating temperature, the wire is going to sag half a meter past the legal limit over a railway crossing.
Oh, man. Here's where it gets really interesting, because in transmission engineering, nothing exists in isolation. It is a massive web of cause and effect.
A total domino effect.
Yeah. To fix that railway clearance, the electrical engineer says, just raise the wire attachment point on the tower.
But moving the wire up changes the center of gravity and increases the wind moment on the structure.
So the structural engineer has to completely redesign the steel lattice.
Exactly. And the heavier, modified tower now exerts a greater load on the soil.
Which means the civil engineer has to rip out the freshly poured concrete and design a larger foundation.
Yes. A single clearance violation discovered late triggers a devastating chain reaction across every discipline. The site grinds to a halt. The contractor files a massive financial claim for the delay.
And the project costs just skyrocket.
This is why the integration of LiDAR data into PLS CAD is revolutionary. You are not guessing based on old survey maps. You have millions of laser data points representing the exact height of that railway gantry, every tree, and every intersecting power line.
So the multidisciplinary team can simulate the maximum thermal sag and check the electrical clearance on a computer screen months before a shovel ever hits the dirt.
Because the cheapest problem is the problem discovered before construction.
I love that quote. The cheapest problem is the problem discovered before construction. That makes perfect sense for catching errors.
But let me push back on the software's authority for a moment.
Because it is tempting to think that whatever design the software spits out as the cheapest is automatically the one we should build. Is the absolute lowest cost design generated by PLS CAD always the right engineering decision?
Definitively no. And relying blindly on the software to make that judgment is dangerous. We have to look beyond CapEx and consider the life cycle costs.
The OpEx.
Right, the OpEx. For example, the software might tell you that using a smaller diameter conductor wire saves you crores in upfront material costs.
Okay, cheaper wire.
But that smaller wire has higher electrical resistance. Over cubic year lifespan, the I squared are electrical losses, the energy wasted, as heat will cost the utility millions and millions of rupees in lost power.
So the cheapest construction option is not always the cheapest life cycle solution. Engineering optimization is a balancing act.
Yes. You are weighing the initial construction cost against safety, long-term reliability, maintainability, and strict statutory compliance.
Like the ASCE 10 for lattice structures, or the specific loading criteria mandated by utilities like Power Grid Corp.
Exactly. And we must clearly define the boundaries of digital design. PLS CAD is a phenomenal structural and geospatial calculator. But what it cannot do is replace a detailed, boots-on-the-ground geotechnical investigation.
Right, the software doesn't know it's under the dirt.
Exactly. It might assume standard soil, but if your contractor hits solid granite 2 meters down, your foundation costs are going to change drastically.
And the software does not negotiate land acquisition with farmers.
No, and it does not secure your environmental approvals. It provides the exact loading and spatial information to support those activities, but human engineering judgment is still the primary driver.
So let's bring this down to the absolute bottom line for you, the listener. You are the design engineer. The project manager brings you into their office, points to the budget, and demands to know exactly how much money your PLS CAD modeling saved the project.
Yeah.
How do you actually answer that?
Well, you never start by talking about the software. You start by showing them the engineering decisions. You lay out the original proposed 200-kilometer route, and then you show them the optimized 196-kilometer route that avoided the protected wetland.
Right.
You show them the specialized crossing arrangement you designed over the highway, and point out the specific foundation rework you avoided because you caught a clearance violation in the 3D model.
You present the balanced sag tension span optimization that prevented them from over-ordering heavy angle towers.
Exactly. You quantify the better decisions, the reduced quantities, and the eliminated execution risk. That is your cost savings.
It is about front-loading the intelligence. By giving engineers incredibly precise data on terrain, tower spotting, the physics of sag tension, and statutory clearances, the platform allows the team to design it right digitally,
Before they have to pay to build it physically,
shrinking the CapEx, execution, and indirect cost buckets all at the same time.
it fundamentally changes the risk profile of infrastructure development. And, if we step back and look at the bigger picture, this methodology raises a deeply fascinating question for the future. If we can build incredibly precise digital twins of massive 100-crore transmission lines to predict and eliminate physical failures and financial waste before ground is even broken, how might this philosophy revolutionize other complex systems in our lives?
Oh, wow.
Right. Imagine applying this level of predictive, multidisciplinary modeling to urban planning, water distribution networks, or even our own personal long-term decision-making.
What else in our world is just waiting to be digitally simulated and optimized before we commit to the permanent physical cost?
Simulate the problem before you pay for the mistake.
That is brilliant. If you are listening to this and you are involved in any kind of complex system design, that is a principle worth taking back to your team tomorrow. Thank you for joining us on this deep dive. Keep questioning how the world is built, keep exploring the mechanics behind the curtain, and we will catch you on the next one.